Assalamualaikum warahmatullahi wabarakatuh, and hello everyone. Today, regarding group project CHM 256, we are choose volumetric analysis to determine of calcium carbonate in eggshell by using back titration. Before we start, I would like to introduce our group members, which is we have Omar Hazik, Haiman Zakawi, Amar Hakimi, Ifwat, and me, Muhammad Ismail Hakim, and our pretty lecturer, which is Dr. Nolia binti Ali. Eggshell are primarily composed of calcium carbonate, CaCO3, making up about 94% of their dry weight. We are used a few methods to determine the calcium carbonate in eggshell. First, volumetric analysis, titration, and back titration.
Volumetric analysis refers to the method of quantitative chemical analysis to determine the amount of analyte by measuring the volume of the analyte with a non-standardized solution. Volumetric analysis is done in the form of titration, where there is 4 types, but for this we will be focusing on acid-base titration. Titration is done when titrant, a standard reagent of known concentration, is added into a solution containing the analyte formulated until a chemical reaction occurs between the titrant and analyte. This chemical reaction usually comes in the form of color change done by inserting an indicator into the solution containing the analyte. There is 2 types of titration: direct titration and back titration. Direct titration is done by adding titrant directly into the analyte until a complete reaction occurs in the form of color change by the indicator. Back titration occurs when the titrant was added excessively, consuming the analyte, resulting in an excess titrant that can be used to determine the analyte through a second standardized solution. Back titration is used for 3 reasons. The first is when the chemical reaction will result in a short, sharp endpoint. The second, the acid or base in the chemical reaction is insoluble in salt. And lastly, the chemical reaction of the titration will occur slowly. An example of back titration can be seen here between calcium hydroxide, which is the analyte, and hydrochloric acid, which is the titrant. The titrant will be added into the analyte excessively, which it then will be titrated by using sodium carbonate to determine the amount of hydrochloric acid used in the first equation.
There's a few facts about eggshell. First, mostly it made from calcium carbonate, CaCO3. It has an outer shell and different color. Calcium in eggshell. Chicken eggshell are about 94% calcium carbonate, CaCO3, with an average shell weight of 5.5 grams. Lower CaCO3 levels lead to weaker shell and are influenced by the hen's age, genetic housing, and mineral nutrition. Function of eggshell: for protection, infection barrier, gas exchange, calcium source, and moisture regulation. There's a few examples of eggshell: chicken's egg, ostrich egg, quail egg, emu's egg, and turtle's egg.
Objective is to determine the percentage of calcium carbonate in eggshell. How titration is used? The titration method that we use is back titration, where the concentration of CaCO3 was determined by reacting it with excess HCl. The remaining excess HCl then being titrated with NaOH. So this is our balance equation. First equation is NaOH plus HCl. So our product will be NaCl plus H2O. Our second equation is CaCO3 plus 2HCl, and our product is CaCl plus CO2.
The apparatus for the preparation and standardization of sodium hydroxide: beaker, volumetric flask, phenolphthalein indicator, diluted hydrochloric acid, conical flask, and also sodium hydroxide. So for preparation of sodium carbonate, we are using sodium carbonate, analytical balance, beaker, volumetric flask, and dropper. For preparation and standardization of hydrochloric acid, we are using measuring cylinder, volumetric flask, pipette, burette, hydrochloric acid, diluted sodium carbonate, methyl orange indicator, and conical flask. For determination of calcium carbonate in eggshell, we are using the egg, mortar and pestle, conical flask, pipette, analytical balance, burette, diluted hydrochloric acid, diluted sodium hydroxide, and also phenolphthalein indicator. For the methodology of preparation and standardization of hydrochloric acid, we are going to calculate for the volume that we are going to use, that is 2.0702 milliliter. Then we are going to measure it using measuring cylinder, and then we are going to transfer into volumetric flask that already contains some water, and then we are going to dilute the acid using 250 ml of distilled water, and then we are going to use stopper to seal the volumetric flask and mix well by turning the flask upside down a few times in order for the solution to be homogeneous. Then we are going to pipette 25 ml of sodium carbonate in conical flask, and we are going to drop 2 to 3 drops of methyl orange indicator, and then we are going to titrate the sodium carbonate with the HCl in the burette. So we are going to repeat 3 times and record all readings and calculate the exact molarity of HCl solution. For preparation and standardization of sodium hydroxide, we are going to calculate for the mass that we are going to use, that is 1 gram, and then we are going to weigh it, dissolve it in beaker, and then transfer it into volumetric flask, and then we are going to add 250 ml of distilled water. Then we are going to use a stopper and then turn upside down to be it mixed perfectly, and then we are going to titrate it. We are going to pipette 20 ml of hydrochloric acid into conical flask, and then we are going to add 2 to 3 drops of phenolphthalein, and then we are going to titrate it with an LH that fill in the burette until the color changes to light pink, and then we are going to repeat 2 more times and record all the readings in the table, and we are going to calculate the exact molarity of sodium hydroxide. For the preparation of sodium carbonate, we are going to calculate for the mass that we are going to use, that is 1.3249 gram, and then we are going to dissolve it in a beaker, and then we are going to transfer it into volumetric flask, and then we are going to add distilled water until it reaches the end point, and then we are going to use the stopper to mix the solution perfectly. And then for the determination of calcium carbonate in eggshell, we are going to use an egg. We are going to heat and dry it for 10 minutes, and then we are going to grind the eggshell, and then we are going to weigh 1 gram of eggshell into 3 different flasks, and then we are going to pipette 50 ml of hydrochloric acid into the flask that contain the shell, and then we are going to titrate it with the sodium hydroxide that contained in the burette until we are going to do the titration until the color changes to light pink.
This is the result and data of the standardization of HCl solution. This is the calculation to find the molarity of the HCl. This is the result and data of standardization of the NaOH solution. Now, this is the calculation to find the molarity of the NaOH. Now, this slide is the result and the data analysis of the eggshell. Weight of eggshell is 1 gram. The data from the Richel Townley. Now, the is the calculation to find the number of mole axis HCl reacted with CaCO3 using HAP and AOH. There is the initial mole HCl. From equation 1, we find the mole of NaOH and number of mole unreacted HCl. Now, we find the number of mole reacted HCl and mass CaCO3 in eggshell. From equation 2, number of mole CaCO3 can find, and the mass of CaCO3 can find by the following calculation. Now, this is the percentage CaCO3 weight over weight, which is 9.1%. In conclusion, theoretically, the percentage of CaCO3 for 1 gram of eggshell is 17.09%. And, however, from the calculation, we obtain 9.1%. From that, we calculate the percentage error is 46.75%. So, we assume that eggshell that we use in this experiment is from an old hen that is deficient in mineral nutrition.
Example of reference that we use to complete our group project. Thank you.